A very good evening to you all. Welcome to the session where we are covering grade 12 physical science paper 2. That's the chemistry paper for your mid-year exam prep. Welcome to everyone who's here. Good to see you guys again. You'll be with me for the second time this week. We did a paper 1 session on Monday altogether, and today we're doing paper 2 for grade 12s. We also have a grade 10 session, if I'm not mistaken. Taffy will correct me, happening at the same time, but at a different link. So welcome to everyone who is here today. My name is Ernest Rangaka, and I'll be your facilitator for the day. I'm going to take you guys through some of the topics that we are going to cover. A few ground rules. Let me just get my screen share up. A few ground rules. So remember, if you've never been with a session in a session with me, I encourage a lot of interaction. So there's guys on Zoom who are with us. Welcome, welcome, welcome. A massive thank you for being here with us. We also are live on TikTok as well. Before I go further, just confirm that you guys can hear me. I don't know whoever's on the team on my side, Theo, Taffy, can you guys hear me?
Yes, we can.
Awesome. Thanks, Taffy. Yeah. Apologies, guys. I'm healing from a cold. I'm better than I was on Monday, definitely, but it's still kind of tapering off. So, key thing, lots of interaction is what I'm going to request from you guys, meaning I want to get feedback. This is a session that we're having together, right? So, oftentimes in the lesson, I will be requesting you guys to partake, either by posting emojis in the chat or answering a question in the chat, or just letting me know that you guys are with me through multiple means. Okay, awesome. That's number one. Number two, sharing is caring, right? So for us to be here today, we want to help as many learners as the learning space team as possible, right? So please just take a moment right now. Let's take a pause. If you were here on Monday, you know how awesome these sessions are going to be. So just take a pause right now. Quickly, if there's a friend of yours that you know is going to benefit from this session, let's pause right now. Quickly send them the link. So if you are on Zoom, you can literally share the invite from Zoom. The link you used to join, just share it with a friend right now. If you are on TikTok as well, just click share live and like make sure that your friends are here so that we can join. This is the beginning of the session. We're going to be here for 2 hours at least. Monday was meant to be 2 hours, but we ended up finishing closer to 9 o'clock. I'm going to try and be tighter with time today, however, right? Just so I can get you guys prepped as best as possible. Other than that, I want to see if you guys are all with me. To make sure that you guys are with me, please make sure that you can access your chat function. So one of the things I'll be asking you guys to do is to just engage with me through the chat. So how do you engage through the chat? So sometimes I'll say, give me an answer A, B, C, D, and then you'll post the answer in the chat. Then I'll say, maybe give me a quick celebration if you got the quick question right. Then you'll post like a reaction, give me a thumbs up, give me a fire emoji, give me a dancing emoji. So I want to just check that you guys are here with me. So please just post the emoji that best describes how you're feeling about chemistry for grade 12. Quickly in the chat, I'll give you guys 30 seconds. Post any emoji that tells me how you feel about the chemistry grade 12 topics. I'll give you guys 10 seconds. Quickly post them in the chat. Even the guys on TikTok, please post them in the chat. There we go. Thanks, Gabetsui. Thanks for the Zoom reactions as well there. You guys are awesome. Okay, people are feeling good. People are feeling good. Awesome. Thanks, Busi. Thanks, Oratile. Thanks, Elan as well, and Blessing. Okay, people are feeling good. TikTok guys, I know you guys will catch up. Just post in the chat. Faith says, good evening. Good evening, Faith. Hope you're doing well. GM says, please start. Yep, we've started. I hope you're still there in the session waiting for us. All right, fantastic, guys. So I'm going to kick off the session with a poll, right? So, reason being, there's 4 topics you guys have covered so far for your June exam. I can't cover all 4 topics in 2 hours. I want to rather cover those topics in a way that's going to be most effective for you guys. So the topics that we have are organic chemistry. So you're talking about naming, you're talking about organic reactions, organic properties, that kind of thing. There's rate of reaction, there's chemical equilibrium, there's acids and bases. So what I want you guys to do is I want you guys to tell me which 2 topics you need the most help with of those 4. I'm prepared to do all 4, right? But I want to try and say, let's take 2 of the topics and let's do justice with those 2 topics, right? So I quickly want you guys to post. So if you're on Zoom, you'll see on your screen a poll just came up. Just select two of the four topics. Don't select all four, please. Just select two of the four topics. And then if you don't know how to use the poll, just post in the chat. And then we'll just look at it there. Same thing on TikTok as well. Please just go there and specify which topic do you need the most help with. Between organic chemistry, rate and extent of reaction, chemical equilibrium, and acids and bases, which topic do you need the most help with? Okay, we'll give you guys another 30 seconds. Have a think about it quickly. If you're on Zoom, there's a poll on your screen. Just complete the poll. Please only select two topics, right? If you're on TikTok, post any two of those four topics: organic chemistry, rate and extent of reaction, chemical equilibrium, and acids and bases. So those are the four options you've got. Quickly post. Thank you, Sam, there on TikTok for posting acids and bases. So far, yeah, acids and bases is winning by a long margin. And then second place, we were almost tied for organic chem and chemical equilibrium, but organic chem just sort of overtook it. And then rates, I think, is last. Let's check in the chat if it changes anything. Right. So let's check in the chat, the Zoom chat. We've got equilibrium, equilibrium, rates, equilibrium, rates and equilibrium, acids and bases, organic and equilibrium, equilibrium and rates and equilibrium, acids and bases, equilibrium and rates of reaction. Okay, thanks for everyone in the chat on Zoom. If you are on Zoom and you post it in the chat, please just pull up the poll. If you don't see the poll on your screen, somewhere at the bottom, you should get options. Click more and then just click poll, and the poll will come back up. And then just enter it on the poll because then it's how the voting went for the session. Okay, we got 15 more seconds. We got more answers on TikTok as well there. Oratilo says rates. Putty says chemical reactions. Putty, do you mean chemical equilibrium? You just said chemical reactions. All of chemistry involves chemical reactions. Busi says rates. Constance says rates as well. Okay. All right, quickly, guys, get your answers in. 5 more seconds, and then I'm gonna then pick and then choose. Okay, at this point, it seems chemical equilibrium seems to be winning. All right. And second place tied is rates and acids and bases. Okay, Putty says rates of reaction. Awesome. Thank you, Busi, for liking the live. You guys are awesome. If you guys are not following us on TikTok, please do. If you're on the live and you're not following us, please, yeah, follow us. If you're on Zoom and you're not following us on TikTok, please follow us. It's at the Learning Space ZA. You'll find lots of awesome content. We do bite-sized posts of quick lessons, so we'll cover a lot of past paper questions on there as well. And as you guys have seen, if you've joined any of our other sessions, we had a grade 11 session live yesterday. We are getting more presenters on, meaning we're going to start being able to do more lessons and more videos for you guys. So please make sure you guys follow us and you just share the content that we've got there. Awesome. I'm going to end the poll now, guys, just so we've got time to start. As we do that, I'm going to just get my screen share going, and then I'm going to start us off with our multiple choice, and then I'm going to just tally up all the votes. And then once I've tallied up the votes, we are going to get to a point where we will then pick the topics. So I'm quickly going to get my screen share up so I can give you guys your little practice questions for the day. It's just 3 multiple choice questions, nothing hectic. I'm going to give you the question on screen, and all I want you guys to do is say A, B, C, or D, and then I will come back and help you figure out which one was the correct one. After the 3 practice sessions to questions to get you warmed up, we're going to then go straight into content. How the sessions run, if you've never been with us before, is that I will take you through a summary of the topic, just a quick overview of the key things to know about the topic, how to approach certain questions in the topic, and then we will do a past paper question. So a question that's going to be similar to what you'll find in your guys' exams that are coming up. Some of you guys are writing on Friday, some of you guys are writing sometime next week, and then we'll go through those questions together, right? Okay, I'm going to share my screen quickly. Give me 2 seconds. Okay, I think my screen should be up. Someone on admin Taffy just confirmed that you guys can see my screen. Taffy or Theo, anyone on our team, just confirm that you can see the screen. Yes, thumbs up. Okay, thanks, Gia, for that. Awesome, guys. Let's get started. Thank you, Sam, and thank you, yeah, for your guys' answers there on TikTok. All right, so we're gonna then be jumping into this. So again, welcome to our Term 2 exam prep. As I mentioned, I'm your presenter today, Mr. Ernest Rangaka, and we will be jumping. So quick, again, rules before we get started. Remember, this is an interactive session. So please use the chat or Q&A functions for questions. So on Zoom, you've got a chat and Q&A. And then on TikTok, you just have a chat function. Also, use your reactions and emojis to participate. If you want to ask a question directly, raise a hand and you'll be given a chance to ask. So even though on Zoom we are looking at a webinar, we do have the ability to then bring you into the session and let you speak and ask your questions, right? So if you have a question that you want to ask, sometimes someone will ask a question and I might not understand the question. I'll maybe then just request you to just unmute and then ask the question live so that we can see it properly. All right. Now that we've got that there, let's get started, right? Okay, so I'm going to give you guys the very first question for the day. Before we get started, I'm going to switch my video off just to save you guys a little bit of data if you are on Zoom. But I'll be there and you'll see this ugly face again at the end of the day. Okay, question number 1 for the day. Right, so we've got this question here. It says, for which one of the following molecular formulae are chain isomers possible? Very, very important. For which one of the following molecular formulae are chain isomers possible? So A, you got C4H10, B, you got C3H8, C, you got C2H6O, and D, you got C3H8O. I'll give you guys 2 minutes. All I want you to do is post A, B, C, or D in the chat to give me your answer. Once all the answers are in, I will then come back and then correct you guys and show you how to go about these questions. Okay, you've got just over 2 minutes. Thanks, Keya and Busi, for your very quick fingers. Also, the guys on TikTok, if you've just joined us, please, there's a question on screen. Just quickly go look at the question and then post in the chat A, B, C, or D. Remember, guys, active learning is the best way to learn and gain knowledge. So if you go and you engage and you try something, even if you get it wrong, that's fine. Worst case scenario today is I will give you the correct answer. So make sure you do active learning. Thank you, Mpo, there for your answer on TikTok, so that you don't, if you sit back and you passively try and engage, you might end up, getting a little bit, but you're not going to get as much as if you take part. Awesome, guys. So Mpile, thank you so much. Thanks, Carlotta. Thanks, Mbe. Thanks, Ponso, there for your answers. I'll give you guys, you still have, look at it thoroughly, 45 more seconds. You've got time, take your time, just quickly go through it and try and find the right answer. No pressure. If you have just joined us, welcome, guys. We're doing paper 2, physical science, which is the chemistry paper for grade 12, helping you guys prepare for your June exam. I will announce the topics we're going to be covering just now. We did a poll to see, because in term 2, you guys covered organic chemistry, rate of reaction, chemical equilibrium, and acids and bases. And then we're going to pick 2 of those topics for me to start off with. And then after that, if there's time, I'll try pick maybe a third topic that I can then take on with you guys. All right. Thank you for all the answers in the chat. 15 more seconds quickly, guys. If you don't know the answer, this is the best time to just go and guess, right? That's what I'll say to you right now. If you're not sure about the answer, just guess. Never leave a multiple choice question blank. Rather guess at the end of the session than leave the question blank, which is pretty important. Okay, 5 more seconds to go. 4, 3, 2, 1. Thank you to everyone for their answers in the chat. Let's quickly have a look, right, at how this question can work out. So we're given 4 possible options, right? We're looking for chain isomers. So first question is going to be in your head, what is a chain isomer? So chain isomer, first of all, isomers are 2 molecules with the same molecular formula, meaning you write them the same way, C3H4, C4H10, but you draw them differently. So they've got different structural formulae, right? Very important. Now, when you're thinking about a chain isomer, the question is, well, how does a chain isomer really work? So we've got a C4, C3, C2, and a C3H8O. So let's try and look at just the first one, right? So C4H10, we have, let's draw something that looks like this. I've got 4 carbons on my screen, if you guys can see them. And then I'm going to have 10 hydrogens to go with my 4 carbons. So I'll have, let me quickly draw all 10 of my hydrogens like that. That's one isomer of C4H10. Now, here's the key thing. Some people want to come and do this and call it an isomer. So I'll show you now what some people do. They take this carbon at the end, right? And then they will move this carbon and then say, oh, no, look, I've now created a little chain at the end. And they make it into this little L shape and say, some people will say that's one methyl propane. That's not true, right? Because my longest chain is still going to be four. The difference is that it's just going to move like that. So you can't necessarily do that because you still have four carbons in a row. So that doesn't work, right? But what could work is if you move that carbon off there and put it somewhere on the off to the side there in the middle, which in that case there, that definitely is a chain isomer because you've now changed it from butane to 2-methyl propane, right? If you've got something like that. So that's something that you definitely can do. So by exploring that, we saw that yes, I definitely can turn A into a chain isomer, right? So I know my answer is A, but let's double check and make sure that none of the other ones can become chain isomers, right? So when I've got B, C, and D, I've only got three carbons. One, two, three. Now, when you're looking at three carbons, there's something that needs to be very apparent to you. When I've got three carbons and I move one of my carbons, let's say I move this carbon, ooh, sorry about that. Let's say I move that carbon off there and I put that carbon here. Well, I didn't really do anything. I still have three carbons sitting like that, right? So I didn't really do anything there. It doesn't really change much. That's still a propane molecule. So let's maybe then say, okay, well, fine. What if I take that carbon instead of moving it to the second carbon and I move it to the first carbon? I put this carbon here. Again, you didn't really do anything. So you just created another propane. The difference is that your L is a little bit backwards. So again, you can see with three carbons, there's not much you can do to change your setup there. So in this case here, you are not going to be able to then make a chain isomer of that one there. And then you can easily see that with two carbons, you're not going to have the same thing. If you couldn't do it with three, you won't be able to do it with two. You're just rearranging carbons. So again, and then the same thing here with the C3H8O, there, you're not going to be able to do that very effectively. To get a chain isomer because you're not going to be able to change the chain length with two or three carbons at play. So with C and D, you can have positional isomers, but not chain isomers. So that's how I want you guys to go through multiple choice questions, right? Notice how it's very important that I didn't just say, oh, I think A is the answer and move on. I figured out which one was the answer, and then I had to also convince myself as to why the other ones can't be the answer. That's the right way to go through multiple choice. And the reason why you might find multiple choice a bit challenging is probably because your content knowledge might not need necessarily be exactly where it needs to be, but that's why we exist at the learning space to help you guys improve your content knowledge. So make sure you join more of our lives, and then we'll help you guys improve the content knowledge. If you guys got the right answer, that is A, please give yourselves some fire emojis, dancing emojis, whatever way you want to celebrate in the chat or give me reactions. If you didn't get it right, but you see where you went wrong, that is also cause for celebration because you guys just learned something great. So also give yourselves round of applause, give yourself some kind of emoji to celebrate the fact that you now know how to do this question. Awesome. Thank you for all the reactions there on Zoom. You guys are epic. Fantastic. I'm going to jump on to the next question. And again, just a reminder, if you have questions, please ask them as we go. So you can post your questions in the chat and in the Q&A. I will pause as we go along to just check through the questions, and then I'll answer them when I do my Q&A session. Awesome, guys. Fantastic. Thanks, guys. Let's go to the next question now. The next question is going to be as follows. I hope you guys can see it clearly. So it says there, consider the following reaction that takes, consider the following reaction that reaches equilibrium in a beaker. So you've got your chromate ion plus hydrogen giving you a dichromate ion plus water. A few drops of concentrated sodium hydroxide are now added to the beaker. All right. Which one of the following combinations correctly identifies the disturbance of the system, which is the first column, and the system's response to that same disturbance? That's going to be the second part. So all I want you guys to do is put A, B, C, or D in the chat. I'll give you guys 2 minutes to do this question. Quickly check it out, see how it works for you guys, and then we'll do the corrections. Okay, if you guys have just joined us, welcome, welcome, welcome. We are doing a grade 12 physical science paper 2, that is chemistry, exam prep for June. We're just starting with some multiple choice questions to warm you guys up. And then we're going to jump into content just now. Someone said there, I can't see, it's blurry. I've got a device next to me, who's that, Tsapang, that I'm testing the connection on. So I can see it on the other side. I think it's just your connection. So maybe just exit and join the session again, or try move somewhere in your space to a space with a slightly better connection. But if I am mistaken, someone in the team, Taffy, Tsapa, Theo, just tell me if you guys are seeing my screen fine. But I've got a device on the side that seems to show it okay on my end. Awesome. So if you've just joined, there's a question on the screen. Please just put your answers in the chat. Write down A, B, C, or D. And then after the 2 minutes is up, I'm going to then do the corrections with you guys and show you how to do it. But it's important, you must commit your answers first. And then I will come back and I will correct you guys. Cool. You guys have 90 seconds left. Thank you, Elam. Thank you, Spusi. So for your guys' quick fingers. Thank you, Sam, on TikTok for quick fingers there. And thank you, Mpo. Sorry. You guys are awesome there. Thanks, Puti, as well. Thanks, Sia and Ponzo and Umpile and Ofensa for your guys' quick fingers. Thank you for your answers. Guys, you got 45 seconds left to answer this question. Thank you, Constance. Thanks to Melo and Oratile and Grace for your guys' answers there. Okay. 15 seconds left. If you are still unsure, you're a bit confused, this is your time to just rather guess, right? Time is almost up. Rather just guess the answer, because it's important to never, ever, ever, ever leave multiple choice question blank, right? You have to always leave it, give an answer for multiple choice. Never leave it blank. Quickly put your guesses in the chat. 5, 4, 3, 2, one. Sorry, someone did ask, and I'll answer the question now that it's time for us to go to do the question together, right? So someone's question was, I don't know who the person is. I just see 3 dots, so I don't see what your name is. But they said, sir, was it added to the reactant side or the product side? Okay, it's a really good question, right? And I love people that have the bravery to ask a question like this. So remember, when we look at the question, it says, consider the following reaction, right? It says that the reaction reaches equilibrium in a beaker. So we have a beaker. This beaker sits there like that. And what did I do? I added some CrO2 minus, my chromium ions or whatever, wherever they came from, and I added some hydrogen ions wherever they came from. They will start reacting and producing some of my reactants, right, in the same vessel. But basically, you've got one vessel that's got all of these things in solution, right? You can see there you've got chromate ions in solution, you've got hydrogen ions in solution, you've got dichromate ions in solution, and you've got water as whatever's suspended in that particular case there. So everything is in one solution. So when they say something is added, what am I doing? I'm just adding that thing to my beaker, right? It's being added to the beaker that we're engaging with. So that's the key thing. It's not added to one side or the other. It's added to my solution. And then you need to figure out, well, how will this thing affect what's happening? So let's quickly look at the solution together. Now, we have this set up here. So a few drops of concentrated sodium hydroxide. So let's try and figure out what is the importance of this, right? So sodium hydroxide is something, it's a particular kind of substance. Quickly post in the chat, what kind of substance is sodium hydroxide? I'll give you guys a hint. I'll make it a multiple choice question. Is sodium hydroxide an acid or is it a base? Quickly post in the chat, is sodium hydroxide an acid or a base? Akum with the quick fingers, thank you so much. And Riatil as well. Sodium hydroxide is a base. You guys are correct, right? Now, when we think about acids and bases, what does sodium hydroxide do, right? Are bases proton acceptors or proton donors? Thank you, Constance, for your answer there on TikTok as well, right? Putis is a strong base. Well done for that as well. Thanks, Khonze and Lady, for your answers. Are bases proton acceptors or proton donors? That's my next question. Exactly, right? So Akum and Radid also got their answers right there. Bases are proton acceptors, meaning they will then, if there's an H plus somewhere, that's our proton, they will react with that H plus. They will take that H plus up. So this question looked like, is this equilibrium? Is acids and bases? Look at how now they're bringing in an acids and bases aspect to an equilibrium question. And this is the thing I've been trying to get a lot of learners that I teach to understand for a while now, right? If you are writing a DBE exam, DBE often used to give questions that were very straightforward, but now they're doing this very IEB-like thing where you take multiple topics and you ask them together. And I want you guys to get to learn this thing really, really, really well. So whenever I now add an acid to this container, I mean a base to this container, it will then react with whatever H plus is going to be in the reaction. It'll take up. So essentially, what's going to happen is the concentration of my H plus is going to go down. That is very important. The concentration of H plus is going to go down in this case here, right? So that is my disturbance, right? Concentration of H plus is going to go down. That's my disturbance. So already what we can see there, my possible answers are going to be maybe A, maybe B, but already I know it can't be C, it can't be D. Just from that fact alone, I know what the disturbance is going to be. Hope that makes sense to you guys so far, right? And I hope you guys still have A or B as a possible answer. Now that's the first step then. Then we need to look at, well, what is the system's response going to be? So looking at Le Chatelier's principle, if the concentration of H plus, right, is brought down, is decreased, the system will respond in a way as to counteract that disturbance. So by counteracting an H plus concentration decrease, I want to do what? I want to increase the concentration of H plus. I want to make more H plus. How do I go about making more H plus? I want to favor the reaction where H plus is a product of that reaction. So we can very clearly see here that my reverse reaction has H plus as a product. That's what's going to allow me to make more H plus. That being the reverse reaction, meaning now I know that A cannot be an answer because A said forward reaction. The correct one that I'm actually looking for is B, where H plus decreases, and as a result, the system wants to increase H plus by favoring the reaction that will produce H plus. That is going to be the reaction that has H plus as a product, giving us a reverse reaction. If you guys got the right answer being B, give yourselves a massive round of applause. If you didn't, but see exactly where you went wrong, please give yourselves fire emojis, give yourselves dancing emojis, whatever celebration you've got there. Hope that makes sense. I'm going to quickly repeat this one because there was a lot that was happening with this question, just so you guys have a bit of an understanding, right? So I'm going to read the question from the beginning. The question then says, consider the following reaction that reaches equilibrium in a beaker. We've got chromate ions, right? We've got hydrogen ions. They react to form dichromate ions and water. Now, in this beaker, we add a few drops of concentrated sodium hydroxide. First thing to note is sodium hydroxide is a strong base, right? The Bronsted-Lowry model says bases are proton acceptors. Now, in this particular case here, we do have a proton in our midst, right? This H plus is the proton. So whenever you add a base and there's a proton, that base will then accept or react with that base. Meaning, when it uses up the H plus, the concentration of our H plus comes down. That's how we knew that C and D cannot be the answers. It's going to be either A or B because the H plus concentration will decrease when you add the strong base. The next part is then figuring out how is the system going to respond to this, right? So we say, okay, let's see what happens. We know what Le Chatelier's principle states, right? When a disturbance is introduced to a system, the system will shift its equilibrium position to counteract that disturbance, favoring the reaction that undoes everything. So in this case now, we can see that if we decrease the concentration of H plus, Le Chatelier's principle is going to react in a way to undo that, to increase the concentration of H plus by favoring a reaction that has H plus as a product. Meaning, I'm looking at my reverse reaction because my reverse reaction will have H plus as a product, and when that has a higher rate of reaction, it will increase the concentration of H plus in my beaker, meaning B becomes my answer. Thank you guys so much for your guys' answers there and your reactions. You guys are awesome. Let's jump onto the last multiple choice question before we do the content for the day. Okay, last question there. Let me just double check that there aren't any questions in the Q&A. No, there aren't. Let's move right along. Okay. The last question looks as follows. We've got a potential energy diagram for a chemical reaction. All right. So when we're looking at this potential energy diagram, let me just move. There we go. That there, then you guys can see it. Theo, I don't know if you're the one that's doing the TikTok. Do you mind just zooming out a little bit? The question is, it seems cropped on TikTok, just so that you can see the full question on TikTok, right? Um, I'll quickly wait for you to do that. Or let me zoom out so that it is visible on TikTok for everyone. Zoom out some more. Okay, but yeah, Theo, please, if you can zoom out on TikTok just so that they can see the full question, right? So the potential energy diagram is there for a chemical reaction. We see potential energy on the y-axis and the course of reaction, or time essentially, on the x-axis. Which one of the following combinations is correct for the forward reaction? So they're asking, what is the value of delta H? Is it y minus x or x minus y? What is the value of the activation energy? Is it z plus y, z minus y, z minus y, or z? What is the value of the potential energy of the activated complex? Is it z plus y, or is it z minus y? I'll give you guys that as a quick one to look at. Once you've looked at that there, try give your answers in the chat, A, B, C, or D, just as a quick one. Thank you to Kia, Akum, Tato, and Sia for your very quick fingers there. Thank you, Sissy Po, as well on TikTok for your quick fingers. And thank you, Melissa, for liking the live. Don't forget to share, guys. So you like the live, follow us, and also share so that people can also join and on our lesson and help you guys prepare and nail your term two. Remember, guys, some universities will accept term two results just to help boost your grade 11 term 4 results. So this is also a very important term to make sure you do well. So make sure you guys really are going to work hard with this one there. Thank you, Sisipo, for sharing the live. Really appreciate it. Thank you, Busi, for your quick fingers there. Thanks, Gilbert, Blessing, and Sapang. Thanks, Boo, for your answers. Thanks, Diakeni. Okay, guys, we've got 30 more seconds to quickly look at this problem. You've got a problem on the screen if you've just joined us. There are 4 options. You need to look at what is the delta H, the enthalpy or the heat of reaction, what is my activation energy, and what is the potential energy of the activated complex. Thanks, Bonton and Pila, for your answers, as well as Ruboni and Grace. Okay, we've got 10 seconds left. If you're not sure, guys, at this point, please just guess and put something down. Never, ever, ever, ever leave a multiple choice question blank. Never leave a multiple choice question blank. Rather just guess, put something down. 5, 4, 3, 2, and 1. All right. So we are done now. Let's quickly have a look at this particular problem. So it says the potential energy diagram for a chemical reaction is shown below. We see it there. Which one of the following combinations is correct for the forward reaction? So when we look at this problem now, when we think forward reaction, right, we need to think how is this going to affect what I'm working with. So when they say for the forward reaction, I'm looking from left to right. If they said reverse reaction, I was going to be looking from right to left. Okay, so from left to right, I'm going to have my reactants there. How do you read this diagram? So this is the potential energy of my reactants. Then energy is added to my system. Up top, there's my activated complex. Then I'm going to release energy, which is called energy of product formation. And at the bottom here, I've got the energy of my products, right? So from energy of my reactants, up to the top where my activated complex is, that's what we refer to as our activation energy. And then from the top down to the bottom to energy of my products, that's what we call the energy of product formation. And then from the very beginning, energy of my reactants down to energy of my products, that difference there is what we call our delta H, right? So let's try and map out what each of these things are, then we can see which is the correct answer. So let's start with delta H. Delta H is going to be from here all the way down to there, right? That's going to be where our delta H is. So when we look at our delta H, we need to try and see which one are we particularly looking at there. So the delta H is going to be final minus initial. So the product energy of my products minus energy of my reactants. So that's going to be X minus Y. So I'm going to say, well, delta H here is going to be X minus Y. That's the heat of my reaction. Let's look at our activation energy, right? Activation energy, I'm going to do in this orangey brown color. Activation energy, as I said, it's going to be the energy that I put in. So it's going to be basically the energy from my reactants here all the way up to my activated complex, right? That is going to be my activation energy. So in that case there, the energy from here all the way down to there is going to be Z minus Y. So my activation energy, we refer to that as the EA or E activation, is going to be Z minus Y. And then finally, the potential energy of the activated complex, I'll do that in red, that is going to be the potential energy at this point. So that's simply going to be Z, right? So that's simply going to be Z. And then all I can do there is take my values, plug them in, and see which one satisfies all of that. Okay, so let's start with delta H. We worked out and said delta H on our side is going to be X minus Y. So immediately with that, I know it can't be A, it can't be B, because I guessed X minus Y. So it's going to either be C or D. All right, I've eliminated two of them already. Then I need to look at my activation energy. Activation energy, I said is going to be Z minus Y, right? It's going to be the difference between activated complex and my energy of my reactants. So Z minus Y, let's see. So Z minus Y is going to be B or C. So already I know that it's not A, it's B or C. I already said it can't be B and it can't be D. I didn't even need to look at the last one to be able to answer this because already I can see that C will be my correct answer. But let's just double check and make sure we do have everything correct in that case there. Finally, we said our activated complex, right? The potential energy at the activated complex is going to be the value that we find right up at the top there, which is simply Z. And we did see that it is indeed Z. And our final answer is C. Awesome, guys. I hope you guys got the right answer. If you got the right answer, give yourselves a massive celebration in the chat and in the reactions. But if you cannot, if you could not get it right, but you do see how the right answer is achieved now, that's also cause for celebration. So give yourself some good celebrations, you know, fireworks, thumbs up, give me a gym muscle, give me a dancing emoji, fire emoji, whatever it is. I see all the emojis there. Thank you so much, guys. You guys are epic. I'm really enjoying it. Someone there said they can't see D. Apologies. I must just check with the team. Sorry, I know that TikTok is a bit zoomed in. Let me just try and get in touch with the guys I've got there on my side. There we go. Perfect. Theo, if you are there on TikTok, please zoom out a little bit more. So I think what I need you to do, I'm going to zoom in this question and then make sure you can see the top of the question that says potential energy, and then you can see until the bottom. Zoom out until you see the whole question. Then at least I know throughout my problem, they'll be able to see everything that's there. I'll just give you a second to do that, and then I'm going to jump on to the next question. So this was the last multiple choice question now that we were doing, just to get us a little bit warm and to get us really working through everything. While we're adjusting everything there on TikTok, we're gonna then look at look at how we answered the poll, right? So let me quickly get the poll results up. Someone did put Q&A. Debuheng just gave the celebrations there. Thank you so much, Debuheng. Really appreciate it. I'm gonna get the poll results up, right? So when I look at my poll results, here, what I can see is most people voted for chemical equilibrium. So I will definitely start with that. The next highest votes were for rate and extent of reaction, followed by acids and bases, and then what got the least number of votes was organic chemistry. So at the end of the day, the democracy is going to win, and I'm gonna start off with chemical equilibrium, right? Cool. Thank you guys so much for participating with that. And if you didn't get a chance to vote, it's because you didn't come to class on time. And if you come to class on time, you get the benefits of being able to be consulted for things like this. Awesome. And the guys who were here on time will get the benefit of their topics being addressed first. All right, let's jump into some chemical equilibrium. Give me 2 seconds to get my notes out, and then we will get started. Fantastic. All right. Now that we've got that there, those that know and understand how I'll run my session, we're going to start off with some definitions first and foremost. After the definitions, sorry for my notes, they seem to be a little bit blurry on my side, but I will read them out to you guys as well. And then we'll try and figure out. I think we had an issue. Theo, we had that. Um, what's this? The WhatsApp community that we started. We'll try and share the link to that WhatsApp community again today. I tried to share it, but I didn't see if it had gone through. So we'll just try and work that. So if you join our WhatsApp community, for anyone who's in grade 12, trying to really improve your maths and science marks, we'll share a lot of information there with you guys, and we'll be able to also. So the notes I take, everything that I'm sharing on this live lesson, I'm going to post that there. The lesson recordings, we'll post that in our WhatsApp community. So please, make sure to join the WhatsApp community. I'll just ask someone in the team to just post links to the WhatsApp community on TikTok as well as on Zoom, so we can see it there. Um, Someone's asking me to zoom out. Sorry, Reggie, I noticed my notes are a little bit blurry within the notes. I'll try, I think it's just the screenshot that I used, but I'll read them out for you. Don't stress, right? So just make sure you do listen out clearly. Um, and let's go. So chemical equilibrium. So first of all, we're dealing with our definitions, right? So from a definitions perspective, open systems constantly interact with their environments, whereas closed systems are isolated from their environments. That's the first thing to know. So for example, a sealed container is a closed system, but an open system is something like an open container. That's going to be an open system. Then you've got reversible reactions, which are important to know. So, in a reversible reaction, the reactants can form products, and then the products can be converted back into reactants. That's an example of a reversible reaction. That's something that's good to know in that point there. Then we also represent reversible reactions with a double arrow. So you'll see A plus B equals, or double arrow, C plus D in that case there. Then lastly, not lastly, but the next one is going to be dynamic equilibrium, right? That is when the rate of the forward reaction is equal to the rate of the reverse reaction. So whenever they're saying a forward reaction is favored or a reverse reaction is favored, remember that when dealing with chemical equilibrium, in a reversible reaction, both reactions are always taking place. So if we said forward reaction is favored, it simply means the rate of the forward reaction is higher than the rate of the reverse reaction. And then if the reverse reaction is favored, it means the rate of the reverse reaction is higher than that of the forward reaction. But they're both happening at the same time. So dynamic equilibrium is when those rates are now equal, right? When the forward reaction and the reverse reaction are happening at the same rate, meaning I'm creating two oxygen molecules and then using up two oxygen molecules every second similarly. So, i.e., think the forward reaction turns reactants into products just as quickly as the reverse one turns products back into reactants in that case there. That's why we call it dynamic equilibrium. The dynamic means they're all happening. Equilibrium means the net concentrations don't really change. Okay. So let's see in this case here. So the reaction rates versus the amount of reactants versus the amount of products. So when my forward reaction is equal to my reverse reaction, right? That's in this case here. What you find is that the amount of reactants remains constant, the amount of products remain constant, right, relative to each other. But if my forward reaction is bigger than my reverse reaction or greater, that is when my forward reaction is favored. So our reactants will decrease and our product will increase. That's when you say the forward reaction is favored. But if a reverse reaction is favored or it's greater than the forward reaction, you'll see the amount of reactants will increase, the amount of products will decrease. That becomes very important for us to note there. And then we need to then come back and think and look at Le Chatelier's principle, right? So when looking at Le Chatelier's principle, then it goes as follows. It says when the disturbance is imposed on a closed system in equilibrium, the system establishes a new equilibrium by favoring the reaction that opposes the disturbance. Only the factors that influence the position of the equilibrium, sorry, the only factors that influence the position of the equilibrium are temperature, concentration, and pressure. Those are your three factors. Some people like to say catalyst. Catalyst does not affect your equilibrium position. It only affects how quickly you can get to equilibrium, right? So here's a suggested layout for how to think about your dynamic equilibrium and Le Chatelier's principle questions. So you must start by stating the disturbance. Then you must say how Le Chatelier's principle will react or how the system will react. Then you must state which one was favored and why is it favored. Then you must also then say what the result of that is going to be. So, does it shift the equilibrium left or right? Does it increase the product? Does it increase the reactants? That kind of thing. That's how you need to answer Le Chatelier's principal questions. Okay, and then we'll go through some of the examples just now as well. So let's take an example of the Haber process. So how we go about making ammonia, right? Sorry, someone just said there. Sorry, in the chat, please resend the WhatsApp link. It is there. We can just try. Okay, I'll just try and paste it there for everyone. Okay, it's been reposted there. And then someone says, please can you repeat how we answer? So when you asked, explain by means of Le Chatelier's principle what's going to happen. So you're going to state four key things. The first thing you will state is the disturbance. So you say, when a system is, so let's actually do an example. Let me do an example, then I'll show you how we go about this. So for an example, we're going to have um, the Haber process. So let me find a blank page and then do this with you and give you a quick look at how this is going to be done. So let's say we've got here nitrogen plus hydrogen giving us ammonia, right? Let's quickly move this out a little bit. There we go. Okay, so there's, the factors that affect our equilibrium. It's going to either be concentration, we can have pressure, and we can have temperature. So with concentration, right? When the concentration of something is increased, the system will respond to always try and decrease it, favoring the reaction that uses it up, that moves away from that side. Or if something is decreased, you're going to want to increase that thing by favoring the reaction that makes up, that makes more of that substance. And then before you are able to answer any of these questions, you must ensure that your reactions are always balanced. So when we look at this one here, N2, NH3, that isn't balanced. I need to put a 2 here, that my nitrogen is a balance, but then hydrogen, I've got 6 there, but only 2 here. So I'll put a 3 here. And then I know I do have a balanced case there. And the reason why this thing must be balanced is because when you're looking at pressure, pressure requires you to know how many moles are on each side. So when you think about pressure, an increase in pressure will make the system want to decrease the pressure. How does the system decrease pressure? It decreases pressure by favoring the reaction that takes more moles and makes less moles. What do I mean by that? Let's look at this example here. On the left-hand side of my reaction, I've got 1 mole of nitrogen and 3 moles of hydrogen, giving me 4 moles in total of stuff. On the right-hand side, I've got 2 moles of ammonia, giving me in total 2 moles of stuff. So my forward reaction takes 4 moles and makes 2 moles. It takes more and makes less. Forward reaction in this case decreases pressure. My reverse reaction takes 2 moles and makes 4 moles. It takes less things and makes more things. It will increase pressure. It will fill up my container a little bit more, right? Or it'll fill up my mixture with, it'll have more moles of stuff in my system. So when pressure is increased, you want to do the opposite. You want to decrease it by favoring the reaction that takes more and makes less, right? But if pressure is decreased, you want to undo that. You want to increase pressure by favoring the reaction that takes less and makes more. Hope that makes sense to you guys. And then finally, when we're dealing with temperature, so this reaction, we would have to be given the enthalpy of that reaction, right? So in this case here, let's say this delta H is less than zero. So we're given that this is an exothermic reaction, right? So exothermic reaction means it releases excess heat. One of the ways I find easy for myself is when given an exothermic reaction, I always go there and I write plus heat or plus temperature. And now you can almost treat this like a concentration problem. Because now you know if I add temperature, right? So if I increase the concentration of temperature, I add temperature, the reaction was going to act in a way to try and take that temperature down by favoring the reverse reaction, which uses up my temperature. If my temperature is decreased, I'm going to want to increase temperature by favoring the forward reaction in this case, because the forward reaction increases temperature, it adds temperature. So that's another easy way of looking at this is that when you get given an exothermic or endothermic reaction, specify which side adds temperature. So if it's endothermic, endothermic reactions are going to add temperature on the reactant side because you need heat to get the whole thing going, or you need energy to get the whole thing going. All right. Someone asked a question there. So which reaction will be favored in pressure? So let's look at this particular one. So let's do an example. Yeah. So our example here is what happens to my system, right, if I increase the pressure. So let's go back and practice how to actually answer the questions. So the first thing you're going to do is you're going to state the disturbance, right? So you'll say, well, when my pressure is increased, then the next thing is you say, well, how does the Chatelier's principle or how does the system respond? When pressure in my system is increased, the system will respond in a way as to try and decrease the pressure of the system. Then you're going to say, well, which reaction is favored when I decrease pressure? So let's look at this one here. So the reactant side, I've got 4 moles. Product side, I've got 2 moles. So to decrease pressure, I want to get rid of stuff. I want to take more and make it less. So in this case here, from the more to the less side, that's going to be reactant side to product side, meaning I'm going to favor a forward reaction. So here, I'm going to favor my forward reaction. And what is the result? The result is my equilibrium shifts to the right. The result is I get more ammonia and less nitrogen and less hydrogen, essentially. That's what happens. So that's what I was saying there. Let's quickly also, we looked at temperature and concentration. We are going to do a full past paper question, by the way. I'm just giving you guys a little bit of the theory up front, so that we can just get a bit of a sense of it, right? So the other thing I want you guys to quickly look at is our equilibrium constant, what does it mean? And then equilibrium graphs and how we basically work with those, right? So equilibrium constant again is just a measure of the extent of my reaction. What do I mean by that? I mean, how far did my reaction go? Do I have more reactants or do I have more products, right? So remember that your equilibrium constant, your Kc, is going to be basically calculated by concentration of products divided by concentration of reactants. So when you have a Kc value, you'll have a value that's going to be either, if you had a Kc value of 1, it means I've got the same number of products as I do have reactants. If you've got a high value Kc, it means my equilibrium is very far to the right. I've got many more products than I do have reactants. So many products, few reactants. But if I've got a low Kc value, my equilibrium lies to the left. So a value that's less than 1, right? Means I've got more reactants than less products. But if your Kc value is more than 1, it means you've got more products, less reactants. Okay, and then note also that Kc is going to be set at, so they'll say the Kc for the reaction is set at a temperature of 200 degrees Celsius because Kc is only affected, right, by a change in temperature. But if the temperature doesn't change, the Kc value will always be the same for a particular reaction. So if a change in temperature favors a forward reaction, my Kc will increase. If a change in temperature favors a reverse reaction, my Kc will decrease. And I already said how to then go about calculating Kc. And what's important in that case there as well is to note that in a Kc calculation, we do not include liquids, we do not include solids, right? Those are incompressible. They don't necessarily have a concentration as such. So if you come back and look at the reaction we were playing with there, how would we calculate the Kc for that reaction? So when this reaction is written out completely, let me quickly do this just so that I can put the phase symbols for this reaction. So the phase symbols for this reaction would be as follows. Okay, so that would be a gas. That would be a gas, and that would also be a gas. So I then say, well, Kc is the concentration of my products divided by the concentration of my reactants, right? Please note, you don't get marks for this. This line here has no marks at all. I write it down just to remember what the reaction is. Where you do get marks is when you start to substitute the values in there, right? Where you get marks is to say, well, okay, let's unpack that. So Kc, what are my products? I've got the concentration of NH3. And then don't forget, the coefficient in front becomes the power up at the top, right? So you must square that out. And then I'm going to look at my reactants. My reactants again, nitrogen, is it a gas or is it aqueous solution? Yes, it is. So then I will put it in there. So then divided by the concentration of my nitrogen. The coefficient in front of that is a 1, meaning the power will also just be a 1, times the other one is going to be my hydrogen. So in that case there, the concentration of H2, the coefficient in front of H2 is a 3, meaning the power in my calculation needs to be a 3 as well. And this is where you get marks. So that will give you a mark. Please note, writing Kc is the concentration of products over concentration of reactants does not give you a mark. Where you do get a mark is by interpreting your reaction and writing the Kc equation correctly. That does give you marks. Okay, awesome. Now let's look at, then from there you would do a rise table, and the rise table will be able to help you how to plug the values in. I'll do an example of a rise table with you guys now as we do the problem that we're going to be facing, right? Okay, and then that again lastly takes us to then equilibrium graphs. Just a quick one to show you guys the graphs. Remember, equilibrium graphs, there's two types. We've got rate versus time. So a rate of reaction versus time graph. That's the graph where you'll see equilibrium happens when the two lines touch each other. That's going to be a rate versus time graph, right? You'll see equilibrium happens when the two graphs touch each other. That's a rate versus time graph. The other kind of graph is going to be an amount or concentration versus time graph. And in that case there, equilibrium happens when the two lines are parallel. So that's equilibrium. That's also another point where we've reached equilibrium, right? So that's very important for us to note. There's two types of equilibrium graphs. Hopefully we'll get a chance to play around with them in the question we're going to try together. Awesome. Right, let's jump straight into our questions now. I'm going to then move to that question that we're going to try, and then we'll do it together. So the question is now on screen, and we're going to work on this question together. So question 6 is what we've got there. And question 6 then says to us, right? Question 6 says, 1 mole of pure hydrogen iodide gas, HI, is sealed in a 1 decimeter cubed container at 721 degrees, 721 Kelvin. Equilibrium is reached according to the following balanced equation. 2HI becomes H2 plus I2. It is found that 0.11 moles of iodine gas are present at equilibrium. Okay, then the question then says, state Le Chatelier's principle in words. That's very easy. We mentioned it together. What I'm going to try and do is just quickly paste the answer there. It'll just be the quickest thing I can do. My handwriting is absolutely hideous, and you guys don't want to see what my handwriting looks like, I promise you. Those that were here on Monday saw my handwriting, and they know that my handwriting is not the best. Right? So let me quickly put down I'll paste that one there. Okay, so there's the definition we've got there. Le Chatelier's principle in words says, when the equilibrium in a closed system is disturbed, the system will reinstate a new equilibrium by favoring the reaction that will cancel or oppose the disturbance. Right? Very, very important, and you get 2 marks for that definition. Nice and easy, guys. Please don't sleep on your definitions. Make sure you guys learn the definitions. If you leave definitions out, you will lose very critical and very important marks. So it's important that you guys spend time working on your definitions. Very, very important. Okay. 6.2 then says, determine the number of moles of each of the following at equilibrium, right? So 6.2.1, they want us to find the number of moles of hydrogen gas at equilibrium. So we are told here that we have 0.11 moles of iodine gas are present at equilibrium. And then all we were given as well there is that 1 mole of pure hydrogen iodide gas is sealed in a container, right? Container at that case there. Equilibrium is reached according to the following reaction. So we need to go and figure out how many moles of these are at equilibrium. So we have at equilibrium 0.11 moles of I2 present. So let's try and see how we can work through this, right? If it's a simple equilibrium problem, this is where we can start drawing our rice tables for the very first time, right? So when we draw our rice table, we will do it as follows. So let me quickly try and draw my table. Okay, and then we've got R, I, C, E, and then at the end, we're going to be looking at our equilibrium concentrations, right? So that's going to be our ratio. I is going to be initial, C will be the change, and E will be our equilibrium values. And then we need to look at what that reaction is. So 2HI plus H2 plus I2, let's put that down there. That becomes H2 plus I2. So when looking at the ratio of that, right? Okay, there's my rice table there. The reason why I draw my double line where the double arrows are, it reminds me to change the sign when I cross over for the change column. So I'm doing this one didn't necessarily need us to do a rice table, but I just want us to get practice of working on these rice tables, right? So let's quickly look at this. So what is the original mole ratio? There's 2 of these, 1 of these, and 1 of these, right? That's the mole ratio that we're dealing with there. Now, I means the initial. So what were the initial values, right? We're told there 1 mole of hydrogen iodide gas is sealed in a 1 decimeter cubed container. So initially, we had 1 mole of this, and let's read this thing properly. 1 mole is sealed in a container, meaning there was nothing else because it was sealed by itself, right? So that tells us now that we are allowed to then say 0 here and 0 there. Don't always assume 0 unless you specify to that it was sealed by itself in a container. If you don't know what it is, then you're going to have to plug in X's and try and solve them otherwise. Okay, we've done that there. Then we're told here that it is found that 0.11 moles of iodine are present at equilibrium. So at equilibrium, I've got 0.11 moles of iodine. So let's quickly go down there. So iodine is at I2. At equilibrium, I've got 0.11 moles of I2, and now I can go finish off my rice table. So when doing my rice table, you need to figure out iodine. I had 0 at the beginning. I now have 0.11. It means I must have gained 0.11 because 0.11 minus 0 is 0.11. Now that I've done that, the most important thing happens. My change column is where I need to then bring all my stoichiometric knowledge to complete that change column. So this change column here, we're going to use stoic. Very, very important. NB, make sure you remember that. NB, the change column is where we use stoic. Okay, sorry, I'm going to quickly just check. There's a question that's there in the chat. Someone says, why 0? Again, I'll quickly repeat why 0 for H2 and I2, because we were told that 1 mole of hydrogen iodide is sealed in a container. So that means they took hydrogen iodide only, sealed it in a container, and there was nothing else. So we know that hydrogen was 0, iodine was 0, because hydrogen iodide was sealed just by itself. Okay. Then we've got that. Now we've got the equilibrium that was given for iodine, and we can now work out what the change was. And we're going to use that change column. We're going to use stoichiometric ratios to find the rest. How do we do that? We're going to use our mole ratios of 1:1, meaning that's how it would have reacted. So in that case there, I know that if I created 0.11 moles of iodine, I would have also created 0.11 moles of hydrogen. It's a 1:1 ratio, right? And then now on the other side, we've got a 1:2 ratio, right? So if there was 1 mole of this that was produced, 2 moles of that had to be used up. So if we get 0.11, this is going to be 0.22, right? That's going to be 0.22. And then let's come back. Remember why I drew this double line here? The double line reminds me that when I cross that line, my signs must change. So here it's going to be minus 0.22. Because I started off with 1, I used up 0.22 to produce the 0.11 and the other 0.11. So I started with this, I used up that, and then I produced this and I produced that. So wherever something's used up, it's a minus. Where it's produced, it's a plus. Where it's produced, it's a plus. Very important. And now we do simple maths, right? And then in this case here, so when we get to this column here, the equilibrium, right? E equals initial plus change, right? Some people like to look at it as ice. We can write it that way as well, where I plus C equals E. That's how you can calculate whatever's there. So I plus C equals E. Think of ice. So very simple. 0 minus 0.22 will give you what? 0.78, right? 0 plus 0.11 gives you 0.11 in that case there. Hope that makes sense and hope that was super easy, guys. Now we can actually go answer the questions that were given to us, right? So 6.2.1, they said, determine the number of moles of each of the following at equilibrium. So at equilibrium, how many moles of hydrogen gas did we have? We did our rice table. We've got that answer on lock. It's going to be 0.11, right? And then again, 6.2.2, how many moles of hydrogen iodide do we have at equilibrium? We did our rice table. So hydrogen iodide at equilibrium, we're looking at this value here. And then all we need to do there is say 0.78. And these will be moles and moles there as well. Awesome. Hope that makes sense, guys. Someone did ask a question. Isn't change measured in moles per decimeter cubed? Change is measured in moles because everything in that case there's moles, right? What's measured in moles per decimeter cubed, let me zoom in, apologies for that, to the rice table. Someone asked, isn't change measured in moles per decimeter cubed? Concentration is measured in moles per decimeter cubed. Change is going to be mole. Everything in my rice table is measured in moles, right? So that's how we basically work through that. Hope that makes sense to you. Awesome. I'm going to jump on to then the next question there. The next question is 6.3. Right. And that 6.3 now tells me that the equilibrium constant, Kc, at 721 Kelvin is 0.02. Right. They've given us that there. The temperature of the container is now increased to 850 Kelvin. The equilibrium constant, the Kc at 850 Kelvin, is 0.09. Is the forward reaction exothermic or endothermic? Okay. They didn't ask for an explanation. They just asked you again, just for that question there. Is it? Oh, the next part asks you exactly why. So in this case there, I'll go back to the notes we had, right? The notes we had gave us this thing cleanly and simple, and it was quite plainly put there. If a change in temperature favors the forward reaction, Kc increases. If a change in temperature favors the reverse reaction, Kc decreases, right? So if a change in temperature favors the forward reaction, what does it tell you? Let me show you here. with this particular reaction there, right? So we have Kc of 0,02 at 721. Then you got Kc of 0,09 at 850 Kelvin. So we can see that when our Kc increases, right, um, temperature also increases. So if temperature increases our Kc, what does it tell us? It tells us that more products are going to be formed at a higher temperature, right? Meaning a higher temperature favors what? It favors the forward reaction. Now, in that case there, when a higher temperature favors a forward reaction, it means the forward reaction is the reaction that gets rid of heat. It gets rid of energy. Now, which reaction absorbs or gets rid of heat? That's the endothermic reaction. Thank you, Busiswe, for your quick answers there. It's the endothermic reaction. Thank you, Busiswe, on the other side as well, for putting that answer down there. Well done. It is the endothermic reaction. So that'll be the answer for 6.3.1. Endothermic, right? Not exothermic in this case here. And then fully explain the answer to question 6.3.1. So I've just said that to you guys, right? So when you think about that, the first thing you must think about is, well, first point is that our Kc increased, right? In this case here. So when Kc increased, what does that really mean for us? So when Kc increased, that means that our products increased. The concentration of our products also increased when Kc increased. All right. Or you can say the concentration of the reactants decreased. But in this case, what's important is the concentration of the products increased when Kc increased. Now, this tells us right now that the increase in temperature, right? Because when Kc increased, remember the temperature increased. So this tells us the increase in temperature favors our forward reaction. That's what that tells us there. Okay. And then to finish this off and then to bring it all together, because according to Le Chatelier's principle, an increase in temperature favors the endothermic reaction. Ooh, apologies for that. Then LCP says an increase in temperature favors the endothermic reaction. And already we said that the forward reaction was favored, so we know that the forward reaction is the same thing as the endothermic reaction. That'll be your thing there. Um, Thanks, Busiswe, as well. Said more products are produced in that case there. Well done. Busiswe, that won't give you the full marks, right? So you must state as much. So you have to give them the full thing. So you must say, well, what we noticed is that when the Kc increased, the products increased, right? Showing us that temperature favors the forward reaction. And Le Chatelier's principle tells us that when we increase temperature, we favor the endothermic reaction. So therefore, the endothermic reaction must be the forward reaction. So that's how you need to put it together there in that case there. And then already we specify that it is the endothermic reaction in 6.3.1. Hope that makes sense to you guys. Let's jump and look at the next question. Okay, 6.3.3, right? 6.3.3 then says calculate the mass of hydrogen iodide present at the new equilibrium at 850 Kelvin. So remember, we did this rise table for the original equilibrium, right? Where we were dealing at, I think it was 721 Kelvin. So when the temperature changed, we reached a new equilibrium. The rise table for the first equilibrium is no longer valid. We have to now deal with a new rise table at the new equilibrium. But then the question becomes, well, how on earth do we do that? Right? How do we be able, how do we work that out and how do we try and get things together there? That's fine. Let's start at a point of saying, well, okay, let's start with a Kc calculation because we did get given a value for Kc. We were told that the new Kc value is now 0,09 at 850 Kelvin. Let's start with that. It's the information that we have at the new equilibrium. Let's start there. So we know that at 850 Kelvin, there's a new Kc, right? So we'll say, okay, cool, that's fine. Kc equals, let's write the equation for Kc, as I told you, concentration of products over reactants. I'm not going to write that. I'm going to write the actual Kc. So my products are going to be, we've got hydrogen, which is a gas. That's good. I also have iodine, which is a gas. No coefficients, to the power of 1, divided by my HI, and there should be a power of 2 because that's got a coefficient of 2. So my Kc calculation will then be my hydrogen times the concentration of my iodine divided by the concentration of my hydrogen iodide. And don't forget to raise that to a power of 2 because we had the coefficient of 2 at that point. That's going to be our first step. It's all we can do. And then the key thing is to then substitute, right? When we substitute here, we're going to need to try and figure out a lot of things. So there's a way of trying to plug these in. But now what I can recommend to you guys is that we're going to use a rise table to be able to figure what these values are going to be, right? What these values are going to be. So let's do this. I'm going to bring up a new rise table. Like I said, the old rise table doesn't work. A new rise table is required to work out the new values there, right? So in our new rise table, the reaction is still the same. It's hydrogen iodide, like that there, two of those, then hydrogen and iodine, right? One of those. So let me just do this. Okay. All right, let's quickly plug that in there. So our ratio is going to be 2, 1, 1. We don't know what our initial values are. We don't know what our change is, and we don't know what our equilibrium values are going to be, right? But what I do know at this point is that when we increased, remember, let's come back here. When we increased Kc, right, we favored a forward reaction. So I know for a fact that from this reaction, when we go in the forward direction, we're going to decrease this and we're going to increase that and we're going to increase that. That's what I do know. So let's try and represent that and use x's to figure out the rest. Remember when we did the first one, I said, if you know for a fact, use absolute values. But if you don't know, don't guess. Rather just put an x and you can work the rest out. So I'm going to use x's in this case to try and figure this one out, right? So when looking at this rise table here, I'm going to do this. So I know that a forward reaction took place, right? A forward reaction took place. So when I do this, I'm going to say, well, I don't know what the initial amounts were, but when you go back and you look at where we ended off, so remember, we ended off here with the last Kc. So we were here, and then things changed from here. So the equilibrium values for our first equilibrium are going to be the initial values for our new equilibrium. So 0,78, 0,11, 0,11. That's where I'm going to start off with everything, right? So I'll have, that's going to be 0,78. That's going to be 0,11, 0,11. That's what I have initially, just, before this temperature was changed. Then a change is going to happen. I don't know what that change is, but I know the ratio in which it will happen. So I'm going to have a forward reaction favored, meaning I'm going to produce reactants, I mean products, right? Let me change this color so it's a bit more apparent. I'm going to produce X, something. I don't know what that is. It's going to be X. And then the mole ratio here is 1 to 1. So I'm going to produce X as well here, right? And then the mole ratio here is 1 is to 2, which means I have to use up 2x to make x. I hope that makes sense to you guys, right? So I start off with these values here. I don't know how much I'm going to use up or I'm going to make, but I do know that a forward reaction will take place. So I'm going to use up x. I'm going to produce x. I'm going to produce x, and I have to use up 2x to produce this x and to produce that x. Okay, hope you guys are still with me. If you're with me, please put a thumbs up reaction or thumbs up emoji so that I know that you guys are there. I don't want you guys to get lost at all with what I'm busy with. Okay, thumbs up on Zoom. Perfect. You guys are still with me. Let's move on. TikTok guys, you guys are quiet. Give me thumbs up so that I know that we can move on, right? Okay. Now that I've got that, let's work out what my equilibrium is going to be. Remember, for equilibrium, it's pretty easy, right? I plus C equals E. In case of emergency, just use that. I plus C equals E. So at equilibrium, I'm going to have 0,11 plus X. For hydrogen, 0,11 plus X. For hydrogen iodide, I'm going to have 0.78 minus 2x. Those are going to be my equilibrium values. And because we were told that the container, I think, is a 1 decimeter cubed container. Yes, it is there. It's a 1 decimeter cubed container. When I work out the concentration, remembering that concentration is number of moles divided by volume, it's going to be the exact same thing. I'm dividing everything by 1, which is my volume. So my concentration will be the same thing as my equilibrium number of moles. So I can simply just take that straight as it is and say my concentration for all of these is going to still be the same, 0.78 minus 2x. That's going to be 0.11 plus x. That's going to be 0.11 plus x. Awesome. Now that I've got my concentrations at my new equilibrium, I'm going to take those and plug them back into our Kc calculation that we had going on here. Because remember what we said? We said we knew what the Kc value was. We were given that Kc value. That Kc value is 0.09. There, we were given that value. So I'm going to now take my equilibrium concentrations, the ones I worked out with my rise table. I'm going to plug those in here because I've got a Kc value, and that will help me solve for x. And once I've solved for x, I'll know exactly now the values I can use and what masses were used, blah, 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 blah. Perfect. Let's jump in and do that, right? So we said a Kc value was given to us as 0.09. So let's plug that in. Wrote that a little bit high. Let's take it down. There we go. Okay, now I need to substitute in the concentration of my hydrogen. So concentration of my hydrogen, we worked out there, that is going to be this one here. 0.11 plus x. Let's quickly put that in there. So that's going to be 0.11 plus x. Concentration of my iodine was the same as well. It was 0.11 plus x. Guys, please remember when you start off with this step, you want square brackets because square brackets show you concentration. But when you substitute, you're now dealing with numerical values. You must use round brackets, not square brackets. Very important. Let's not lose marks by doing silly things, right? And then the concentration of hydrogen iodide, I think that's this one here, 0.78 minus 2x. Let's substitute that one in there. 0.78 minus 2x. Now we need to flex our mathematical muscles, right? Let's flex our mathematical muscles and see how you guys can do with this one. So what I need you guys to do is take that, and we need to now go and solve for x with this particular problem. So you're going to cross multiply, you're going to multiply everything out and then solve for x, right? So remember, the first step here is going to be 0.09 times 0.78 minus 2x, and that then is going to be equal to 0.11 plus x times 0.11 plus x. So it's going to be 0.11 plus x squared. So I want you guys to multiply this thing all out and then solve for x. I'm going to give you guys 3 minutes to do this quickly. Multiply it all out, solve for x, and then let's post our answers for x in the chat. While you guys are busy, I'll just check in the Q&A to see that there aren't any questions. Okay, nothing in the Q&A. So I'll give you guys, yeah, you still have 2.5 minutes to quickly solve for x. Let's find what our value for x is in this case here. Okay, guys, you guys still have just under 2 minutes for this particular problem. What I need you guys to do is multiply those things out, and solve for x. Okay, you still have about 80 seconds to go. The first two answers I get, I'm going to then move on. If you've just joined us on TikTok, there's a problem on the screen. I want you guys to multiply that out and solve for x. Okay, I've got two answers in. They're not the same answers, so I'll wait for another answer that confirms one of those two answers. Okay, guys, I'll give you guys 30 more seconds to another minute. To the two people that come and I can't see the other person's name that have put your answers in, please just double check your answers there. Ratilek has given an answer. And has also given an answer. We're tending towards one place there. Cool. All right, we're tending towards the same answer across the board there. Awesome. Answers are coming in. Okay, last 20 seconds for you guys to finally drop your answers in. I know some of you guys are almost done. This is important that you guys get to do this exercise, especially questions like this, guys. More and more, the basic rice tables that don't have X's, I hardly see those anymore in exams. So oftentimes you'll get rice tables like this. I want you guys to get practice with these questions. Okay, 10 seconds, guys. We're wrapping up now. All right, let's call that, guys, and then put it all together and then try and get to the final answer that we've got there, right? So what you guys should find when you put it all together, you guys should get, I'll double check where you guys might be going wrong, right? But when you do the sum, just for the sake of time, I'll release one where we go through the entire thing, right? So the answer that you should be getting after everything else, right, is x is equal to 0 comma 7, sorry, 0 comma 0.0775. Let's quickly wrap the question up, and then if we've got time at the end, I'll go through that maths quickly. But because you still need to cover a second topic, I'm going to quickly go through it. So the answer you should get is this. So you'll just double check that as soon as you guys are done. And then once you've got that question there, that gives us the x. So remember, when we come back here, we're trying to figure out these x values that we're dealing with, because the question was asking us there to say calculate the mass of hydrogen iodide present at the new equilibrium at that point there. So the mass of hydrogen iodide present, so we're going to take this value here, 0.078, I mean 0.78 minus 2x, right? That's the number of moles of hydrogen iodide. We have to find the mass, right? So when we come back, where am I now? Okay, there. So what we need to do is then substitute that value in there, all right, to be able to then work it out. So remember what we ended up sitting there with the value of the number of moles of hydrogen iodide, or the concentration, but it's 1 mole per decimeter cubed, so we can just use the number of moles of hydrogen iodide. We said we had 0.78 minus 2x, and then we now have a value for x that we can just substitute into that place there. So 0.78 minus 2 times 0.0775. When you've got that there and you plug that together, that should give you 0.63 moles, right? That's how many moles you've got in that case there. But they asked us specifically to go and find out the mass, right? Keeping in mind that the number of moles is equal to mass divided by relative molecular mass. So to find the number, to find the number of grams, or the mass, we then say number of moles times my relative molecular mass, and I can sub those values in. The number of moles we've got from the previous question, we're simply going to just substitute those in there. Once we've got those ones in there, we can then go 0.63 times my relative molecular mass. Hydrogen is 1 and iodine is 127. So you have 1 plus 127, and that's going to give you a final answer of 80.64 grams. So that's the steps that you guys need to take in this particular case there, right? And then you get the mass that you needed to work out for this particular problem. I'll try and go through the next topic. So the next topic, if I go back to my poll, I think rate of reaction might have gotten a higher rating, the next highest rating, because 13 people asked for chemical equilibrium, and then 11 people asked for rate of reaction, and all the other topics had slightly less, 9 and 10 in that case there. So we'll do rates, and then hopefully at the end I can just come back and try show you the maths of how you get to that particular answer for that question there, right? All right, let's quickly then, I think that was the last question for equilibrium. I'm going to quickly jump into rates, and then we'll come back to the maths at the end, because I don't want to take too much people's time if you don't have data to connect for the rest of the session, right? I'll come back to that one. Okay, so I'm going to skip acids and bases, and people ask specifically for rates. So let's quickly jump into rates of reaction. I'll try to do it as quickly as I possibly can, just so we've got time to go back to a question like that. Okay. Reggie says they got 0.12. Reggie, we'll look at that question again afterwards. So I'm giving you, I've done the full calculation. Even when you go look at the memo for that particular problem, it's 0.0775. Remember also, just to do, you need the quadratic formula. So don't forget to do plus and minus in that case there. Very, very important. Cool. Let's quickly go back and then quickly try wrap through rates and extent of reaction. energy and change. So we had a quick look at this. I'm not going to go through this in too much detail. I showed it to you guys when we were doing the multiple choice question, right? How to read your energy profile diagrams, energy of reactants, activated complex, activation energy, heat of reaction or enthalpy, energy of products, and your energy of product formation. I showed you guys how you basically work through that there. The one thing we didn't necessarily go through is how catalysts affect reactions. Remember that a catalyst is going to speed up my reaction without taking part simply by lowering my activation energy. So initially my activation energy was going to be, let's say, all the way up there. When I add a catalyst, it brings my activation energy only down here. So I only need to go up there and come back down. But note that the catalyst doesn't change the energy of your reactants. It doesn't change the energy of your products. It only changes how much energy is required for that reaction to take place. Then let's look at the factors that affect the rate of reaction, and then how does collision theory feed into all of that, right? So the factors that affect our rate of reaction, we're looking at nature of reactants, basically saying that some things are just more reactive than others. It's in the nature of that reactant. If you look at group 1 metals, they're super reactive with water, right? Without needing a lot of extra energy. Group 2 metals can't really react very heavily with water, but they will react with acid. If you want them to react with water, you need to add a bit more energy and then they'll react with water. So some things are just more reactive than others. Surface area is how much contact surface the area there is for the reaction to take place. The more surface area there is, the quicker the rate of your reaction. Concentration is how many moles per unit volume. The more moles per unit volume, the more particles you have that can take part in a reaction, higher rate of reaction. Pressure is really closely linked to concentration, number of moles per unit volume, except for pressure, we're dealing with gases, right? And then temperature, it's the average kinetic energy of the molecules in whatever you're dealing with. So the higher the temperature, the more energy you've got there initially. So you require less energy to then go through your reaction. And then a catalyst we just saw. Catalysts speed up reactions by lowering the activation energy. You're lowering the energy requirements for that particular reaction. So now let's look at collision theory, right? So collision theory, again, the rate of reaction is determined by the number of effective collisions per unit time. So an effective collision is a collision that has got sufficient energy, number one, very important. Also, an effective collision needs to have the correct orientation. So the particles, if they don't have the correct orientation, they'll come A and B will come together. If the orientation wasn't correct, they'll just bounce off and then nothing will happen. But if you have the correct orientation, they'll come together, they'll hit, and they'll actually have an effective collision and form your products. So that's very, very important, right? And then finally, there's this giant graph that we can look at here, or not graph, but table that shows you how each of these now, how collision theory affects each of our factors. So when you think about temperature, right, when dealing with temperature, each collision has got higher average kinetic energy. Your particles also move faster, right? That means temperature means you will have sufficient energy, right? Which means you'll have more collisions per unit time, and that will lead to more effective collisions and a higher rate of reaction. What about surface area, right? Surface area is more contact points for collisions, and more contact points for collisions means you'll have a better chance of getting the correct orientation because you've got more of those there, and that'll give you more collisions per unit time because there's just more things taking part at that point. It doesn't affect energy, but you've got more collisions per unit time and a better chance of getting the correct orientation. That'll lead to a higher rate of reaction. Concentration of pressure means that you've got more particles in the same place, similar to like surface area. When you're reacting, there's more things taking part there, meaning you'll have a better chance at more collisions per unit area. You'll have a better chance at a higher chance of getting correct orientation, giving you more effective collisions. A catalyst, again, in that case there, it decreases the EK that's required for effective collisions, right? Meaning you will have sufficient energy for more particles there. It also does help with orientation, your catalyst, right? Because some things didn't have the correct orientation because the energy at that orientation wasn't enough. But if the energy requirements are lowered, that orientation might actually be now a correct orientation, meaning that'll improve the orientation, more effective collisions per unit time, increased rate of reaction. So that's how we need to go essentially and answer questions in terms of collision theory. Is how does that factor? Is it a factor that affects the energy? Is it a factor that affects the collisions per unit time or the correct orientation? And if that's the effect, it means we'll have more sufficient, or I mean, more effective collisions per unit time, and then we'll have a higher rate of reaction. And then finally, let's quickly look at our Maxwell-Boltzmann distribution curves, right? Where your Maxwell-Boltzmann distribution curve is the curve that shows you the distribution of energy on the y-axis per particle. I mean, sorry, energy on the x-axis per number of particles. So how we see this here is that a lot of particles have very little energy. That's initially. And then very few particles have a lot of energy on the right-hand side there, right? So most particles don't partake in the reactions. These particles here are the only ones that are lucky enough to partake in the reaction. So as we then change the factors that affect equilibrium, I mean, rate of reaction, we can go back and see how these are then will affect our rate of reaction. So what happens when we increase temperature, right? If we assume this line here, right, is going to be the line that determines where the energy requirements. So when you increase temperature, what you're doing is you're giving all of these particles a bit more energy. So the curve is going to flatten out a little bit, and then more particles have got more energy. So essentially these guys here that didn't have enough energy before now do have enough energy, and now they can take part in the reaction. That's what it looks like from an energy perspective. From a concentration perspective, you're not increasing the energy of any one particle, but you're increasing particles overall, right? It's like the population going up. So these guys here, before that didn't have energy to take part in the reaction, now have energy to take part in the reaction, which is important. And then when you add a catalyst, what happens? I'm not increasing the particles. I'm not increasing the energy, so the curve doesn't change at all. However, we're dropping our activation energy here, right? So all of these particles here that couldn't take part in the reaction before can now take part in the reaction. That's how your Maxwell-Boltzmann curve changes for all these various things. And then we went through collision theory. Now let's jump into the questions and then see how we go about answering these questions, right? Try and wrap this up as quickly as we can on our side. So with that in mind, let's quickly jump in to question 5, right? So question 5 is going to be as follows. Question 5 says, consider the following decomposition reaction that takes place in a sealed 2 decimeter cubed container. So we've got 2N2O5 becoming 4 nitrogen dioxide plus oxygen. The graph below shows how the concentrations of N2O5 and NO2 change with time. So in this case here, we see graph A and graph B. They didn't specify which ones, but normally we can tell, right? If we're starting with a lot of this, that's the one that's going to start high and then go down. And when we start with none of that, that's the one that's going to start low and go all the way up, right? Um, then let's quickly go and look at the questions. Refer to the graph above and give a reason why curve A represents the change of concentration of NO2, right? So curve A is the one that's increasing, and give a reason as to why that represents the curve of NO2. So like I said before, our products initially are at 0. So as the reaction takes place, our reactants are going to form products, and that will then increase. So your answer there will simply just be the fact that it started at 0. So the initial concentration of NO2 was 0. That's literally all you have to say. And then the concentration increases thereafter. Oh, sorry about that. Thereafter. Okay. 5.2 then says, consider the statement below, right? The rate of decomposition of N2O5 is half the rate of formation of NO2. So rate of decomposition is how quickly our N2O5 gets used up. That is half that of the NO2. That's what the statement is. Is the statement true or false? And give a reason for your answer. So they said rate of decomposition of N2O5, right? Listen, let me just highlight these. So this is going to be green, and we're looking at that curve over there. And then let's do one in blue, or let's say orange or pink. Let's try to do something different. NO2, and that's going to be this curve over here. All right, so the rate of decomposition of N2O5 is half that of NO2. So without even looking at very many things, all I need to go do is look at my reaction. So when you look at your reaction, two of these react to form four of those. So every time they react, two of these break down and four of these are created. So for every two that go, four are created, meaning the rate of decomposition will be half because 2 divided by 4 is literally a half. So that statement is true, right? Let's quickly go do that. So is the statement true or false? The statement is true. They said, please give a reason, right? So the gradient of the graph of NO2 is twice the gradient of the one for N2O5, or you can make reference to the mole ratio, which tells you in terms of reaction, that's what's going to happen. But essentially, let's refer to the gradient because that's the rate of decomposition rather than the mole ratio. So you say true, and then you'll say, well, the gradient for the NO2 graph is 2 times the gradient for the N2O5 graph. And even if you go back, you can clearly see, I'll even pop out a little ruler, right? So on average, that's about, call that 20 degrees down. It's about 100, nearly 160 degrees, 20 degrees down, right? And that is about 40 degrees up almost, you see, that graph there. So that graph gradient is double the other gradient. Cool. Pretty chilled, nothing too hectic. Then it says there, calculate the mass of NO2 present in the container at 400 seconds, right? So we want to find the mass of NO2 present at 400 seconds. So NO2 is going to be the purple one. At 400 seconds, we're looking at this point here, right? So at that point there, we need to go and read off the graph and say, well, oh, we've got 200 moles per decimeter cubed, so 200 times 10 to the negative 4 moles per decimeter cubed. And we need to then go and use that to calculate. What do they ask for? The mass, right? So in that case there, I know that N is equal to C times V. Let's first find the number of moles, then I can find the mass, right? Or if you want, you can do it all in one step, right? By then saying N is equal to CV, and then N is going to be M over M. So we can do this is equal to C times V. And then you can calculate the mass directly by then saying, well, my mass is going to be equal to C times V times M, essentially. And that will get you the answer in a single step if you want. So let's do that. Let's do it that way. So we said the concentration, we just found it. It was 200. But remember, they said this graph is times 10 to the negative 4 moles per decimeter cubed. So we need to substitute that in there. So concentration is going to be 200 times 10 to the negative 4 times the volume, right? The volume that we've got there. Did they tell us how big the container was? Let's quickly go and look at how big the container is. Yes, we were told it's a 2 decimeter cubed container. That's the volume we're going to use. And the relative molar mass of nitrogen dioxide, in that case there, we can quickly look at our periodic table, and what you will find is that it's going to give you 46, right? So that'll be 46 when you add your two oxygens plus one nitrogen. Okay. And then when we finish this one off here, we can plug that all into our calculator and you guys should get an answer of 1,84 grams. Hope that makes sense to you guys. Let's jump on to the next question from there. So the next question then is going to say, calculate the average rate of decomposition of oxygen in moles per deciliter cubed in 700 seconds. The average rate of decomposition for that, right? So let's try and figure this one out here. So let's quickly go back. The rate of, sorry, quickly go back here. No, not decomposition, sorry. The rate of production of oxygen in 700 seconds. So what we're going to do there is say, well, we don't have something that to tell us directly what happens to the oxygen, right? But what we can do is we can then go and find the rate of production of nitrogen dioxide by using this graph here. And the average is simply going to be from here to there. Once you can find the average rate of production of that, and then we can use our mole ratio to determine then what will that of oxygen be. Knowing that our mole ratio is 4 to 1, whatever answer we get there, we divide it by 4, and that will give us the rate of production of oxygen, right? Cool. So let's take those values there, and then use those values to find the rate of production, right, of oxygen. So what I'm going to do there is say, okay, cool, let's look at those values. So we know we started off at 0, and in 700 seconds, we were able to produce, and then if you take that line, let's quickly take our ruler and draw a line all the way there to see how much we're dealing with. Okay, so in 700 seconds, we were able to produce, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I think these all go up in fives because it's 50 difference. 1, 2, 3, 4, 5, 6 times 5 times 6. 1, 2, 3, 4, 5, 6 is 30. So that's going to be 280. That's what we're going to get there, right? So that's how many, that's the concentration, right, that we had at the end. And then we need to then find the rate of production in moles per decimeter cubed per second. So we know we're dealing with 280 for our nitrogen dioxide. So let's first do that, right, and find the rate of production of nitrogen dioxide. Okay, so then our average rate is going to be our final minus our initial divided by the delta T, right? And then we said our final was going to be 280. Remember, it's times 10 to the negative 4 minus 0 divided by 700 seconds. Once we've got that, we can simply plug that into a calculator, and then you'll find that the answer is going to give you something close to 4 times 10 to the minus 5, right? And that's going to be in moles per decimeter cubed per second. But that is for nitrogen dioxide, right? We need to find that for oxygen, keeping in mind the mole ratio between nitrogen dioxide and oxygen is a mole ratio of 4 is to 1. I'm pretty sure it's 4 to 1. Yes, it is 4 to 1. So to find the average rate for oxygen, we simply divide that by 4. That's going to be 4 times 10 to the negative 5 divided by 4, which will give you, sorry, it's meant to be negative 5, 10 to the negative 5 moles per decimeter cubed per second. Nice and easy, nothing too crazy for this one. Let's quickly look at the next question. All right, so 5.4, the Maxwell-Boltzmann distribution curve for N2O5 initially present in the container is shown below. So we see it there. Then they tell us the initial concentration of N2O5 is now increased. So the concentration goes up. Redraw the distribution curve above in the answer book and label this as P, right? On the same set of axes of the curve, you're going to sketch the one that's obtained for the higher concentration and label this as Q. This one's pretty easy, nothing too hectic. So you're going to just draw one that starts at the same place. It's going to just go a little bit higher and end a little bit higher as well. And then you'll label that Q. Very easy. This one is not a very difficult question for us to do. That's what it would look like as soon as you're done with that. Right? Great. Let's quickly now move on to the last part of this question. The last part of this question then says, will the rate of decomposition of N2O5 at the higher concentration be higher than, lower than, right, or equal to the original rate of decomposition? Explain your answer using collision theory. So what I want you guys to do now is simply post in the chat higher than, lower than, or equal to. So will the rate of decomposition of N2O5 at the higher concentration be higher than, lower than, or equal to the original rate of decomposition? Explain using collision theory. So basically, will the reaction be faster, slower, or the same rate when we increase the concentration? That's roughly what they're asking. So it's write higher than, lower than, or equal to in the chat. I'll give you guys 15 seconds. This one is not a very difficult one. When I increase the concentration, how does that affect my rate of reaction? Simply write higher than, lower than, or equal to. Quickly post that in the chat. 10 seconds to go. Thank you for quick fingers there. Thank you, Sianda. Thank you, Akum and Busisiwe. Thank you very much. Definitely, right? It's going to be higher than. So the minute we do that, increase the concentration, it's going to be higher than. Then they said we need to use collision theory to answer the question, right? So how we go and look at that, we must think about the following thing. So when we increase the concentration of N2O5, right, we will have more particles when the concentration increases per unit volume. What does that mean? That means, right, we are going to then get to a point where we can have more effective collisions per second, because more particles means we have higher chances of getting the correct orientation. Not energy, but we're going to have better chance of getting correct orientation by having more effective collisions, right? So we will then have there more collisions per unit time. In that case there, and in that case there, it will result in higher effective collisions, therefore higher rate of reaction. Awesome. Right, guys, that is the end of the rate question that I was doing there. Okay. It's 8 o'clock now. I really want to maybe try and go through a little bit of one other topic with you guys, just so that I can help you guys a little bit more. I don't mind staying another 30 minutes, to try and touch maybe one more question with you guys. So please let me know, because the other topics were pretty much tied, being organic chemistry and acids and bases, right? So what I'm gonna do now, I'll try and see if I can rerun the poll on Zoom. But now, what I need you guys to do, okay, I relaunched the poll on Zoom, right? You can only choose between acids and bases and organic chemistry because we've done the other two topics. So acids and bases and organic chemistry, you can choose between those two topics, and let's see how it goes. Thank you for the answers that are coming in. If you're joining us on TikTok, you can't see the poll on Zoom. Just say between acids and bases and organic chemistry, which one would you most need help with? Okay, I see people are posting in the chat. Please respond on the poll, especially, but it is noted there, Karabo. Okay, I'll give you guys 10 more seconds to respond to the poll on your phones. If the poll isn't on your phone, what you need to just do there is at the bottom, if you don't see the thing where it says poll, press more and then select poll. It'll come up and then just select the one topic between organic chemistry and acids and bases that you think I need to really help you guys with. Okay, someone says, please don't forget to send the WhatsApp PDF. Yeah, we'll definitely put that in our WhatsApp community. So please make sure you join the WhatsApp community to be able to receive these notes that we are using for the session. I'll also share the full paper that I'm using at the end of the lesson as well, and the memo for that paper. Okay, I'm gonna call it there. So it seems that acids and bases is the one that won. So let's quickly go through that one, right? Cool. Let's jump into some S's and bases. I'm going to do it very quickly, guys. So please just bear with me because I only have about 30 minutes to do it with you guys. I can't stay till very late tonight. I do have a lot of other work I need to get done, but I'm going to try and help you guys as much as I can for S's and bases. So I'll do the notes in about 10 minutes, which will take us to quarter past, and then we'll have 15 minutes to try a question together. All right. So I'm going to be very quick with this, but like I said, I'll share these notes again in the WhatsApp community. So acids and bases, we've got definitions of acids and bases. So we've got the Arrhenius and the Bronsted-Lowry definitions. Arrhenius says acids increase the concentration of H3O plus in water, bases increase the concentration of OH minus in water. Lowry Bronsted or Bronsted-Lowry says acids are proton donors, bases are proton acceptors. Proton is what we refer to as H plus, right? Um, Now, from there, let's also look at some common acids and bases, right? So strong acids, you're looking at nitric acid, hydrochloric acid, sulfuric acid. Strong bases, sodium hydroxide, potassium hydroxide. Weak acids, ethanoic, oxalic, carbonic acids. Weak bases, you're looking at ammonia, potassium carbonate, calcium carbonate, sodium hydrogen carbonate. Those are some of the weak ones, right? Then we can look at what they refer to as monoprotic, polyprotic, and diprotic and triprotic acids. So monoprotic acid is an acid that only has one proton to donate. So like HCl, HNO3, um, as well as your ethanoic acid, only has one H to give. Polyprotic acids is any acid that's got more than one to give. So diprotic and triprotic acids are also polyprotic acids, right? And then there's some like acid-base reactions that we need to then just be aware of. So the base one that we're dealing with is an acid plus a base equals salt and water. But then there's a few others we need to also note of. Acid plus metal will give you salt and hydrogen gas. Acid plus metal oxide will give you salt and water. Acid plus metal hydroxide gives you salt and water. Acid plus metal carbonate will give you salt, water, and carbon dioxide gas, right? So how to remember this in a very quick way. Acid plus base gives salt and water always. But if in your reactants there's no oxygen, you aren't able to produce water. That's why you only produce hydrogen. So you'll get salt and hydrogen. So you can see here, metal oxide, you do have oxygen, so you can produce salt and water, right? Metal hydroxide, you do have oxygen, so you can produce salt and water. Then metal and carbonate, you've got oxygen, but you also have carbon as well, meaning that carbon will bond with oxygen and create an extra carbon dioxide. So there you'll get salt, water, and carbon dioxide. That's a quick way of trying to remember this, right? And then from there, we can go look at the concentration, right, of acids and bases, okay, and also the strength, relative strengths of acids and bases, okay. So now in that case there, a concentrated acid is one that has a large amount per unit volume. A dilute one's got a small amount per unit volume, right? Then we go look at how does that differ from the strength or the weakness of acids and bases. So a strong acid is one that will ionize completely in water or nearly completely in water to form a high concentration of H3O plus ions. Whereas a weak one will only ionize partially to form a low concentration of H3O plus ions in water. A strong base, however, will dissociate completely in water to form a high concentration of OH minus ions, and a weak one will only dissociate partially to create to form a low concentration of minus ions in water. Notice how I also say sometimes I say ionize, other times I'll say dissociate. What is the difference between those two things there? Ionization is where we make ions for the first time, right? So you start off with a covalent bond, you break that thing, the covalent bond up, and an electron is literally transferred in that reaction. That's now a covalent bond that breaks up and the electron is transferred. That's ionization. Dissociation means I had an ionic bond to begin with. So those two were already ions. There's no electron transfer in a dissociation process. So it means Na plus stays Na plus, OH minus stays OH minus. Very, very important there to note in the terminology. Then the other thing I want us to also then go look at is what we refer to as the autoionization of water, right? So autoionization of water is when we're dealing with our Kw equation, right? So autoionization of water is basically what happens is that water is what we refer to as an amphiolite, right? Or amphiprotic or amphoteric. So what does that mean? It means water can be a base or an acid. Now, if water reacts with itself, one water molecule acts as an acid, one water molecule acts as a base, and then water will undergo this autoionization process where you then have an acid reaction and a base reaction happening in one thing from one particular substance. Now, Kw is the equilibrium constant, the Kc value for the autoionization of water. So it's the Kc constant, the Kc value for this particular reaction there. And that Kc value is always constant at a temperature of 25 degrees Celsius. So Kw is going to be equal to 10 to the power of negative 14. And that is also equal to the concentration of OH minus ions times through H3O plus ions. That comes in very handy when we do pH calculations. Um, in that case there. And then also we need to think about indicators, right? So when you do titrations and that kind of thing, we have to think about indicators. Before I go to indicators, let's look at hydrolysis of salts, right? Because that's how we know how to pick the right indicators. So in a neutral reaction, neutralization reaction, such as a titration, right? A salt is one of the products. Now, sometimes that salt can react again with the water and will change the pH of that solution. So the principle to think about here is that the ion from a strong substance is weak, meaning it won't react again with water. And the ion from a weak substance is strong, meaning um, it easily reacts again with the water, right? Now, if you think about a strong acid and a weak base, what you'll end up with there is that you're going to find that the NH4 comes from weak NH3, meaning it's going to react again with water. The NO3 comes from strong HNO3, which does not, so this thing moved up there, it does not react again in that case there. So you are going to get an acidic salt at the end of the day, right? I'll give you a shortcut for this one so we don't waste too much time, right? Strong acid plus weak base will give you an acidic salt. So whichever one of the between the acid and the base is stronger, that's what'll where your salt will essentially be. So strong acid, weak base, your salt will be acidic. Strong base, weak acid, your salt will be basic because your base was stronger. And then if it's strong and strong, you'll end up with a neutral salt because not one is going to be stronger than the other one in that case there. But why that happens is because of this thing that I was telling you guys now there, right? But just to keep it short, whichever one is stronger, that's what your salt will be. Strong acid will give you acidic salt if it's reacting with a weak base. Strong base with a weak acid, basic salt. Strong and strong will give you neutral. Now that you know how to determine the kind of salt that you're dealing with, we can then use that to determine what kind of indicator we can use for particular titrations. So the two key things that are important for titrations is understanding these two principles, what we refer to as an equivalence point and what we refer to as an end point. So the equivalence point of a titration is the point where the acid and the base has reacted with all the base or the acid. Where the end point, however, is when the indicator changes color. To have an effective titration, we want to make sure that the end point matches up with the equivalence point of the reaction you're busy with, right? So here's an example. If you had strong acid, weak base, you know that your salt is going to be acidic. My equivalence point is going to be somewhere in the acidic range, lower than 7. So, like for example, in this range here, I want to use a titrate, an indicator with an endpoint in that space there because my equivalence point is going to be there. So when you know you're going to be dealing with strong acid, weak base, you want to use something like methyl orange because your equivalence point is going to be in the acidic range. You'll pick an indicator that has an endpoint in the acidic range. Then if you have strong and strong, you know you're going to end up somewhere in the neutral range. So I'm going to pick an indicator that has an endpoint that's going to be in the neutral range. If I've got a strong base and a weak acid, my equivalence point will be somewhere in the basic range, higher than 7. So I'll pick an indicator that will give me a range that's going to be higher than 7. That's essentially how you go about picking indicators in this case. Right. And I think that covers in a very short time acids and bases overall. Let's go in and try do one of the questions that we can work with. Right. So the question we're looking at here is going to be question 7. Let's jump straight into question 7. Hopefully we'll be done by 8:30. But thank you for your guys' patience. Right. If you don't have data or time to stay, it's okay. We will be putting this lesson up on our YouTube and you can catch it there. All right. So question 7 then says, 7.1, the conductivity of three acid solutions, A, B, and C, are shown below. It's investigated at the same temperature. The brightness of the bulb in the apparatus shown below is used as a measure of the conductivity of those solutions, right? So we see there's an acid, carbon electrode, and then we want to measure the conductivity, which we will see by the brightness of the bulb. The acid solutions are electrolytes, and then it says define the term electrolyte, right? So to define the term electrolyte, um, electrolyte is basically a substance whose aqueous solution contains ions. That's an electrolyte, right? Let me quickly I'm gonna just copy paste that answer down there. Let me quickly bring that across. I'll quickly type it here. So it's a substance whose aqueous solution contains ions, right? You'll get 2 marks for that. Then the question then says here, um, in which solution, A or B, will the bulb be brighter? Give a reason for your answer by referring to the types of acids. So let's quickly go back up there. So in A or B, which one will be brighter? And then you need to be able to pick there. So A is 1 mole per decimeter cubed of sulfuric acid. B is 1 mole per decimeter cubed of nitric acid, right? Those are both fairly strong acids, right? But in this case, between A and B, A for me will have the brighter light. Reason being, H2SO4 is a diprotic acid. So yes, they're both strong, but it's diprotic, meaning it will donate 2 H pluses for every one that HNO3 will donate, right? So 7.1.2, I say A, reason being H2SO4, let me just zoom in, is diprotic, meaning it will donate double the H plus of HNO3. So you'll have more ions moving through, meaning you end up with a brighter light. All right, so let's look at 7.1.3. 7.1.3 says, in which solution, B or C, will the bulb be brighter? Give a reason for your answer. Let's go see between B and C, where B is nitric acid and C is acetic acid. And in that case there, we are going to pick nitric acid. Why? Because nitric acid is a strong acid, acetic acid is a very weak acid. And now we know that the strong acid will ionize completely, the other one will only ionize partially. And therefore, we will have more ions going through and giving us a brighter light. So for 7.1.3, the answer will be B. B, reason being NO3 is a strong acid that will ionize completely. In that case there, whereas acetic acid will not ionize completely, it'll only ionize partially, right? At that case there. So you can also then say another thing that HNO3 will have a higher Ka value. Awesome. Let's jump on to 7.2. 7.2 then comes and says to us, a hydrochloric acid solution, HCl, is standardized by titrating it against a 25 cubic centimeters of a 0.04 mole per decimeter cubed sodium carbonate solution, Na2CO3. At the end point, it is found that 19.5 centimeters cubed of HCl has reacted. The balanced equation for the reaction is Na2CO3, right? Um, plus HCl, I'm giving you NaCl plus CO2 plus H2O. Calculate the concentration of HCl. So in this case, it's pretty simple. We can use our titration calculation to get this one. Our titration calculation is going to be as follows. Na over Nb equals CaVa over Cb VB, and then we can substitute all of our values in there, right? The number of moles, we just use our mole ratio there. So our acid is going to be 2, our base will be 1, so we'll simply plug in there 2 over 1 is equal to concentration of the acid. We don't know, that's what we need to find in this case here, so we'll leave that as Ca. The volume of our acid, we were told that the volume of our acid is going to be 19.5 centimeters cubed. So that's going to be 19.5 divided by the concentration of our base. Concentration of our base was given to us as 0.04. And the volume of that is going to be 25 cubic centimeters. Please note, right? So some of you guys might be seeing that I didn't convert my volumes. In this equation, it's fine if you don't convert because they are both in the same unit, only for this equation, right? Because basically what you'll do is I'm going to then say, oh, I need to divide both of them by so not divide, multiply. No, divide both of them by 1,000. So I'll say divide that by 1,000, and I'll say divide that by 1,000 as well. But basically, that does nothing. That basically just cancels out anyway. So in this case, only for this equation, it doesn't make it. It doesn't matter if I didn't convert them, because converting them is going to just cancel out at the end of the day anyway, right? And then when you take that and you solve for Ca, what you'll find is that you'll get a value of Ca of 0, comma 0.1, no, yes, 0.10 moles per decimeter cubed. Right? That's what you'll get there. In that case, then the next question comes to us and says, suppose a few drops of water were present in the burette before it was filled with a hydrochloric acid solution. How will the volume of the HCl solution needed to reach the endpoint be affected? Choose from greater than, smaller than, or remains the same. Give a reason for your answer. I want you guys to quickly put that in the chat, what you guys think the answer is. If there were a few drops of water present in the burette before it was filled with hydrochloric acid, how will the volume of HCl solution needed for the endpoint be affected? Greater than, smaller than, or remains the same. Think about how it affects the concentration of my of my HCl solution, and then you can pick out an answer there. 10 seconds to quickly put that one together. Okay, I'll be generous. 20 seconds. 10 seconds left. Okay. No one's put their answers in there. Guys, remember this is it's basically a multiple choice. Whenever they ask you greater than, smaller than, or equal to, it's basically multiple choice. So make sure never to leave that blank, right? Always give an answer. But in this case, the correct answer will be greater than, right? Reason being, the few drops of water that are there are going to in dilute my HCl, right? So the water will dilute the HCl. It'll dilute my HCl, right? Meaning I'll need a greater volume to meet the same number of moles. Okay, perfect. So that's what we've got there. Guys, what I am going to do, apologies. I know it's almost 8:30 now, and I do have another meeting now at 8:30, right? What I'll try and do soon is maybe after my meeting, I'll try record this last part of the question. I know the lesson was meant to end at 8, and I know you guys have stuck around for another 25 minutes, and I do appreciate that. I'll record the last part of this thing and post it up on our TikTok for you guys to watch. But this is giving you a little bit of insight into, especially acids and bases. You got to sort of see how the theory goes there, and then you got to sort of see how our um, conductivity works for acids and bases. You also got to see now here working with diprotic, triprotic, how that affects conductivity, and a very basic as titration. But this is super basic. This is not the one that you're gonna get. The one that you're gonna get is gonna look very much more like what you have in the next part of the question. But I will record that and I will put it up tonight. Just that I've got a meeting right now that I need to attend, and then I'll put that up. So hopefully by 10 p.m. that last part of the question will be up on our TikTok. But thank you guys so much. I really do appreciate your time, and I look forward to seeing you guys soon. Cheers, guys. Please, if you need any more help, go to our YouTube at the Learning Space ZA. You'll find us doing much longer acids and bases lectures, chemical equilibrium, the stuff we didn't get to do today, organic chemistry. You'll find organic chemistry lessons there. So go there and watch those lessons. They'll help you guys for your tests that are coming up. I won't forget to send the notes. I'll quickly resend the link to our WhatsApp community. Join the WhatsApp community, and then I'll post the notes there tonight. As soon as I'm done recording that video, I'll post that up. I'm quickly gonna let me quickly copy and paste this. Here's the link to our WhatsApp community. There we go. I don't know if I can paste it on TikTok. I can try. Yeah, I'd put it on TikTok as well. There's a link to our WhatsApp community. So just join our WhatsApp community. WhatsApp channel, and then we'll be able to post those notes. But it's been an absolutely epic time, guys. I really do appreciate it. Thank you guys for your patience. I know we stayed way longer than we were supposed to be there. Spusto says thank you. Spusto, it is absolutely quite a pleasure, and I'll post that last thing there for you guys as well. Dewang also says thank you. It's a pleasure on my side as well. What I will do is I will post that last question for you guys before 10 p.m. I promise. I finish at 9:30, then I'll be able to post that for you guys. So from me, Ernest, and the Learning Space team, thank you to my team. Thanks, Taffy and Theo, for being there and pulling the late hours to make sure that the African child is not left behind. We will see you guys soon.